Hey, so this is Joe, and this is the first part of the 7th chapter of Stewart's Calculus, and so this whole chapter is going to be advanced integration techniques. So techniques for solving complicated single variable integrals that you wouldn't be able to solve with any of the techniques we've learned before. There are a bunch of them, but probably one of the most useful is integration by parts. And integration by parts, although it sounds like a funky name, really it's just the product rule, which we learned for derivatives, but kind of flipped around and used for integrals. So, if you don't remember the product rule, I'm going to start off from that, because we know that that works, and then kind of go backwards and turn it into the integration by parts, but you'll see it's really the same thing. So, the product rule states that if we have a function h of x that's composed of the product of two functions, f of x times g of x, if we want to get the derivative of h, we find that by saying, okay, well, f prime of x times g of x plus g prime of x times f of x. You change one, do nothing to the other, then add the other one changed plus the first one that remains the same. Let's say we want to get h. We start off with something like this, but we want to get back h of x. Well, we can integrate. So we'd get dx equals the integral of f prime of x g of x plus g prime of x times f of x, and all that dx. Well, remember, we can split up this big integral. Now we've got h of x is equal to the sum of these two integrals right here. Well, h of x is just equal to f of x times g of x. And that's equal to f prime of x, g of x, dx, plus this integral, g prime of x times f of x dx. So, we can subtract one integral over to the other side. And it doesn't really matter which, because these are kind of arbitrarily defined. But so that'll give us f of x times gx is equal to, minus, subtraction sign, the integral of f prime of x gx dx is equal to the integral of g prime of x times f of x dx. And this is the product rule. And so basically what it says is if we see an integral where it looks like two kind of big functions are being multiplied, you call one the derivative and one the normal function. Then you take the derivative of the quote-unquote normal one, and they're arbitrarily defined, but generally you want to be integrating the most complicated function. So you define this one as the most complicated function you can integrate, 1, and the other as the quote-unquote normal function, the f. Then you take the derivative of the f and put it in an integral, multiply it by the integral of the more complicated function, and so that's all in an integral, you multiply it, and then you subtract that from the product of the two quote-unquote normal functions. And you can write it like this. The way I generally like to write out the product rule is this way. So you've got the integral of u dv is equal to uv minus the integral of v du. So the u can be thought of as the quote-unquote normal function, the f of x. The dv can be thought of as the g prime of x with respect to x. And so you'll need to take the derivative of the u to get the du over here, and that du is going to be equal to f prime of x dx. And you have to integrate this v, and you want to define the dv as the most complicated bit of this function to integrate, but one that you can still integrate. That's important. And so you'll get v is equal to g of x, and then you make all these substitutions. So I think that this is the more helpful way to think of it, of the product rule, when you're actually applying it as kind of u and v substitutions. You're just substituting in some part of the function that's being integrated. And so that is the product rule. That's conceptually what it means. Now, I'm just going to do a bunch of problems with you, and they will become clear. And there are a couple of key different kinds of problems, 3 namely, and we're going to do one of each. So, here we go. Alright, so, first we're going to do number 7 on page 492 of your book. And we're asked to evaluate this integral, the integral of the quantity x squared plus 2x times cosine x dx. And this is kind of the easiest, most basic way of doing integration by parts. It's just where you're going to have to do the method once or twice, and then you'll solve the integral, and that's it. And so we clearly have kind of 2 parts of this integral. We've got the x squared plus 2x, and then that's multiplied by the cosine of x, and then the dx is going to go with one or the other, depending on which one you're integrating. So we're going to use our rule of thumb. We're going to be integrating, or calling dv, the most complicated bit that we can integrate here. And this is just a polynomial, not too complicated. The trig function, we'll say that that's a little bit more complicated. And really you could do it either way, just one ends up being easier when you're integrating the thing that's a little bit more difficult. It just happens to work out like that. So u is going to be x squared plus 2x. Our dv is going to be cosine x and then the dx because we're integrating it. And so that will mean that our du is going to be the derivative of this function, so that's 2x plus 2, and then we have to add the dx in there. And then our v, we integrate this, the derivative of sine is cosine, so the integral of cosine is going to be sine of x. And so we'll remember, I'll just write out our little formula here again. If we have u dv, that'll be equal to uv minus the integral of v du. So we'll bring this guy down, and we're just going to make all these substitutions. U times v, that's x squared plus 2x times sine x minus, now the integral of v du, so these two guys. So that is sine x times 2x plus 2 dx. Now, this integral, we still don't know how to solve that. But we can use the integration by parts technique one more time, and then we will be able to solve it, hopefully. If not, then you'll have to do something a little bit more complicated, but I can tell you in advance that this one, you will be able to solve it. So, our u, once again the trig function, let's call it the more difficult one to integrate, so that's not going to be our u. Our u is going to be 2x plus 2, and our dv will be sine x dx. We take the derivative, du will be 2. That's why this reduces down, because you just get a constant. And our v, 2 dx. And then v, the derivative of cosine is negative sine, so the integral of sine is going to be negative cosine x. So now we can do our little substitution again, and remember not to forget this first little bit of the function right there. So bring this down. Minus is going to carry through, and then we got our uv, that's a negative cosine x times 2x plus 2 minus the integral of v du. This negative is going to come out in the coefficient, so negative and a negative is a plus. That 2 can also come out in the coefficient, and this is just going to be the integral of cosine x dx. So this is an integral we can solve right away. And this polynomial, we'll just kind of simplify it a little bit on the next screen. Get a little bit more room here. Alright, so here I've rearranged some of this, distributed out some of the negatives, and now this is going to be minus the integral of cosine x dx. And so we say to ourselves, the derivative of sine is cosine, so the integral of cosine is going to be sine, but there was the 2 out in the coefficient. So we've got 2 sine x, and then remember this is an indefinite integral, so we've got to still add that plus c. You'll get docked like something like a quarter or half a point for not adding that point plus c on the Calc AP exam, so just do it. You just remember to do that. You don't see limits, add the plus c. So that is our first problem, and that's kind of the most simple, or not simple, but the most basic application. And so now we're going to go do a problem where we use integration by parts for definite integrals. And it's not more complicated, you've just got to make sure you get your limits right. So let's go do that. Alright, so we're going to do number 27 on page 492, and it asks us to evaluate the integral from 1 to 3 of r cubed times ln of r dr. And so we don't need to worry about the limits quite yet. Let's just start off by doing integration by parts as we did in the last problem. So let's say that the most complicated thing to integrate, this one it actually doesn't matter, you can do either way. I'd say actually the most complicated is ln of r, but we don't know how to integrate that. So it has to be, dv has to be r cubed. So we'll call u ln of r, dv is going to be r cubed dr, du, that ln of r, we take the derivative, that's just 1 over r dr, and the v is going to be r to the 4th over 4. So we do our uv, ln of r times r to the 4th over 4. Let's make that super explicit. And now wait, remember we have limits. What do we do about this? Well, just put these in a bracket, and eventually you are going to subtract, like put 3 in for r here, and then subtract from that this expression, but evaluated where r is 1. But keep it looking like this for now until we evaluate the limits of everything. And then this minus sign, you can put this outside the brackets because it'll apply for the next limits, because that's really just a coefficient of the integral, and so the integral is still from 1 to 3 v du, so that would be, this r is going to go under here, so that'll turn into an r cubed over 4 dr. Now, we don't need to do integration by parts again, we can solve this integral ourselves. So we've got ln of r to the 4th over 4 between 3 and 1, minus, and then this r cubed becomes an r to the 4th over 4, and the 4 times 4 is a 16. So that's r to the 4th, evaluated between 1 and 3. And so now let's go to evaluate this integral. We'll plug in 3, subtract from where r is 1, and then we'll do the same for this integral as we always do. So we do the substitutions and all the algebra, we'll get 81/4 times the natural log of 3 minus 80 over 16. And I think you'll be able to do that algebra yourself. Just remember that the natural log of 1 is 0, because you have to ask yourself, alright, when does e to the what is equal to 1? Well, anything to the exponent 0 is equal to 1, so e to the 0 is 1. So then ln of 1 is going to be 0. So, but this is the final answer, and that's how you do integration by parts applied to definite integrals. Now we're going to do the hardest kind of integration by parts, and this is where we get have both of the functions in the initial integral are things where the when you take the derivative or the integral, there ends up being a pattern that kind of never ends. And so examples of those are trig functions and functions with e in them. And the method here that we're going to be doing is really write out the entire equation every time and kind of be a little bit clever. But hopefully I will show you how to be clever, and then you'll be able to, it won't be being clever anymore, it'll just be kind of doing it on your own. But so let's go do that problem. Alright, so we've got two functions here. We're asked to evaluate the integral in number 18 of e to the negative theta times cosine 2 theta d theta. Now, both of these functions, you take the derivative, you take the integral, we're going to get a pattern. E to the theta, you take the derivative or integral, it's always going to be something times e to the negative theta. Cosine 2 theta, you take the derivative or the integral, it's always going to be something times cosine or sine of 2 theta. And so we've got this pattern. So what you want to do is, as you're integrating by parts, and you're going to end up doing it 2 or 3 times, you want to always write out the original integral equals, because as you're integrating by parts, you're going to wait until you get an integral, this exact same integral, in the function over here, and then you'll be able to add them or subtract them and cancel them out. But for now, when you assign parts of the function to be u and part to be dv, it doesn't matter which, because there's going to be a pattern for both. Just keep it consistent. So if you're calling dv, the trig function, as you do integration by parts multiple times, continue calling that trig function the dv, and same with the e for the u. And that's what we're going to be doing. We're going to call, and you could do this either way, but this is just how we're going to do it this time. U is going to be e to the negative theta, and dv is going to be cosine 2 theta d theta. And so we're going to get du, take the derivative of that, that's going to be negative e to the negative theta, and the v is going to be 1/2 sine of 2 theta. And so we use the integration by parts formula. That's going to be 1/2 sine 2 theta times e to the negative theta minus the integral of v du. And we can bring out that negative 1/2 that's going to turn out there. So negative and a negative is a positive. So 1/2. That's going to be e to the negative theta sine 2 theta. Oops, I forgot the d theta there. D theta. And now look. This integral is pretty close to that one. However, we've got a sine function here, not a cosine. But if we take the integral of this one more time, we will get a cosine function. So this is going to be an instance where we're only going to need to do the integration by parts twice. So we come down again, and we'll get the integral of e to the negative theta. Cosine 2 theta d theta is going to be equal to, and now we're going to do integration by parts on this integral right here. And so we're going to be consistent with what we're doing up here. The u is still going to be e to the negative theta, and the dv is going to be sine 2 theta d theta. And so we take the derivative of this. Du is going to be negative e to the negative theta. It looks familiar, right? V, we're going to take the integral of this. We say, all right, the derivative of cosine is negative sine. So that will be a negative 1/2 cosine 2 theta. There's a d theta right here. And so don't forget about this little bit of the function. So it's going to be 1/2 sine 2 theta e to the negative theta plus 1/2. And we're going to open up our little brackets right here. So uv is going to be negative e, or negative 1/2. I'm going to squeeze that in there. Negative 1/2 e to the negative theta cosine 2 theta minus, and now we're going to have our coefficient come out here, v du. Actually, that's 3 negative signs, so the negative sign stays, and we're going to have another 1/2, and that will be e to the negative theta times cosine 2 theta d theta. Now this integral is the same integral as this one, so we're going to need to do some algebra to make this come out on its own to the point where we'll be able to add it or subtract it on to this side. So I'm going to work out this algebra for you and to show you what we get. Alright, so it turns out that we get a negative 1/4 of the original integral over here. So we're going to add that 1/4 over to this side, and we will get 5/4 integral of e to the negative theta cosine 2 theta d theta is equal to 1/2 sine 2 theta e to the negative theta minus 1/4 e to the negative theta cosine 2 theta. And all we have to do is multiply this side, or both sides I should say, by 4/5. And we get rid of that, and that is how we evaluate that initial integral. Look, that's the same integral up here. So that's the most complicated application of integration by parts. I hope that was clear. Yeah, I think between these three equations, you've seen just about everything that you're going to have to do using this technique. It's a super helpful one. It'll help you with a lot of different integrals. But stay tuned for the rest of this chapter. It's just going to be more techniques of solving tricky integrals like this. Thanks for watching.